Assalamualaikum and hi. Today I will present about I am Ahmad Fikir Ahmad Azman is C18161. My group partner is Siti Nur Hidayah binti Mazlan A18084. Today we present about our project assignment, which is Unipolar coding, NRZ-L coding, and NRZ invert coding. So first one is about the next slide is about line coding. Line coding translated a set of binary data versus a time domain signal which is suitable for the communication channel. Properties include transmission bandwidth, power efficiency, error detection and correction, transmission voltage and DC component, adequate timing content, and transparency. Line coding type that will be discussed in our slide is unipolar, NRZ-L, and NRZ-I. The first one is unipolar. The positive input value will produce an output of 1, and negative input value will produce an output of 0. Non-return 0 level, which is NRZ-L, positive input value will produce an output of 1, and negative input will produce an output of negative 1. Non-return 0 inverse, which is NRZ-I, positive input value will make the signal wave to go 1 to negative 1, and vice versa to NRZ-L. Negative input value will make the signal wave stay the same for that cycle, copying the previous output. Okay, now we're going to the next slide, which is methodology. This is the methodology for our program. Firstly, there is 7 steps to write this coding, which is the first one. We need to ask the input from the user. For example, like the number of bit, and for each bit that the user wants, we need to decide whether it's going to be high output, which is 1, or low output, which is 0. And then in the next step, we set the program for plot time unipolar, NRZ-L, and NRZ-I. And then the third step is unipolar encoding. In this unipolar encoding, line coding, we set the sample for the encoding 1000 sample. The fourth step is we set the NRZ-L encoding, and the fifth one is we set for the NRZ-I encoding. In this NRZ-L encoding, it is similar from the unipolar encoding, but we change the amplitude of the graph, which is -1 for NRZ-L and 0 for unipolar. Next is decoding. Decoding is a process which is we record the result from the input, and we make it to our output result. And the last one is display and plot output. In this display and plot output, we need to setting and set the graph for unipolar, NRZ-L, and NRZ-I, and then it will display in our MATLAB programming. That's all for me.
So this is the MATLAB coding. The first one is we ask the user to enter the input, and then we do the program setting as Ate just said before, and then we initialize the unipolar, NRZ-L, and NRZ-I graph values as zeros, and then we do the unipolar encoding, where if the input is greater than 0, it will produce 1, and then if it is not greater than 0, it will produce 0. As for NRZ-L encoding, if the input is greater than 0, it will produce 1, and if it is not greater than 0, it will produce -1. So for NRZ-I encoding, it is a little bit different than the previous two. As we said, the last bit is equals to 1 first, and then because we need to set either it is positive or negative value to calculate, so we set it as 1. And then if the input is greater than 0, it will produce minus of the last bit that we have set, and then it will update the last bit to be the opposite sign of the previous last bit, or and if it is not greater than 1, it will just be as the same as previous last bit. So next we have the decoder, where we set the count equals to 0 and the last bit equals to 1, because we need to use the last bit once again. So we do it in looping, just like for the encoder. The line coding program, we just do the repetition until like it completes the cycle of the total number of sample. And then we update the count value, and then we for unipolar decoder result, it will just copy the unipolar line coding output. For NRZ-L, if the line coding output is greater than 0, it will just copy, but if it is not greater than 0, it will change from NRZ-L output, which is -1, into 0. So for the decoder result. So for the NRZ-I, if there is change in last bit, it will produce a decoding output which is 1. If there is no change in last bit, it will produce the output as 0. So we then display the decoding result and plot for each of the graphs with a title and labels. We are using subplot so that it can be shown in one page. So here is the result. We do the example for 8-bit input, which is 11001010. As you can see, for the decoding result below it, it produce the same result as the input. And for the graphs, as I said before, Unipolar, they have 1 and 0 value, whereas it is the same as the input. And then we have NRZ-L, which is similar to Unipolar, but the low value is -1. And then we have NRZ-I, which will toggle from low to high and high to low if there is input of 1, and will stay as the previous output if the input is 0. So the GUI that we have entered in this program is that if the user enter a number other than 1 or 0, it will be read as 1 and 0. By setting that number greater than 0 will be 1, and the rest will be 0. So in conclusion, unipolar and RZL and NRZ-I line coding can be demonstrated and differentiated from each other, as I explained before. NRZ-L and NRZ-I encoding have a higher power loss, where NRZ-L is hard to synchronize and manipulate the transition for a long period. In order to overcome this problem, NRZ-I is used to force the transition to occur. And I think that is all for our presentation. Thank you.